the frequency components will be having a constant magnitude. I mean, the
Yes, ma'am.
signal will be having a constant magnitude,
Yes, ma'am.
right? See,
Yes,
for
ma'am.
this curve, it's a current curve. It's just an inverted V curve, right? When magnitude is rising till this resonant frequency and it is decaying after the resonative frequency, right? But in order to get this constant magnitude of current, will follow this the difference F2 and F1, which is called the bandwidth.
Okay, ma'am.
Okay, gain or
Yes,
the
ma'am.
magnitude of the current is constant. Next, the quality factor or Q factor. For a series resonating circuit, always this quality factor is defined as the ratio of the voltage across inductor or the voltage across capacitor to the applied voltage, either VL by V or VC by V is equals to K. Right? So for the inductor, Q is VL by P or omega L by R, because VL is IXL, XL is omega L. Right? And for the capacitive circuit, Q is VC by V, or we can consider VC as IXC. So it's 1 by omega CR. So these two are the expressions of quality factor or Q factor of the series resonating circuit. So further, by considering omega naught value as 1 by root LC, you can obtain another expression of Q in terms of RLC, and Q can be also be expressed as this one, resonant frequency by bandwidth, the quality factor, that is equals to omega naught by omega 2 minus omega 1, right? Omega naught is the resonating frequency, and what is bandwidth? Omega 2 minus omega 1, or F2 minus F1, right? So it is just F naught by F2 minus F1, quality factor. So quality factor will decide that pure your how pure the selectivity of this circuit. That means depending upon this bandwidth. See, it's just inversely proportional to the bandwidth. That means quality factor will be more if bandwidth is less. That means for a narrow bandwidth, Q factor or the quality factor will be improved. If the bandwidth becomes wider, then what will happen? Quality factor will be reduced. Okay, the Q
Yes,
factor
yes, ma'am.
reduced. Okay, now we'll apply the same principle to this parallel RLC circuit. You can see it's an AC supply voltage connected across R, L, and C. RL are in series, and capacitor is just in parallel with this branch. Okay, or just individually we can separately we can connect RLC in parallel mode. So that will be also called the parallel circuit. Now for this, we will apply the current divider rule, because here the total current I is dividing the two parts, I1 and I2. I1 is passing through RL branch and I2 is passing through capacitor. So just apply the current divider rule, you will get the expression of current I1 and I2. I1 is simply the voltage by the impedance of the branch. What is the voltage? The supply voltage V. What is the impedance? It is just R plus J itself. And what is the current I2? It's just the voltage across capacitor divided by the impedance. So voltage across capacitor is just again equal to V. It is parallelly connected. And what is the impedance? What is the impedance? Z. No resistor is there. So what is the impedance? It will be just equal to the capacitive reactance. What is the capacitive reactance? It is nothing but 1 by J omega C, 1 by XC, or 1 by omega C, or 1 by J omega C. Because the real part is absent, if you express this capacitive reactance in rectangular form, you will get 0 plus 1 by J omega C. Okay. Now 1 by omega C is XC. So it is actually XC by J, right? And 1 by J is nothing but minus J. right? Applying the complex algebra theory. So I2 will be finally V by minus Jx or JV omega c. Any doubt up to this in this derivation? Have you all understood why it is taken as JV omega c? It will be obtained from this V by the capacitive reactance. V by the capacitive reactance. Because in this branch no resistor is there. So R part is 0. That means 0 plus 1 by j omega c, and 1 by j is just replaced by minus j. Okay.
Okay, ma'am.
Now again this
Why
minus
the
j will be
negative sign
replaced
is not there?
by,
Why the negative sign is not there? Minus j if you.
here.
Yes, ma'am.
See, 1 by j is minus j, right? So that minus and this minus will be cancelled out. Again, in this expression, I have taken 1 by j. You can see
Oh,
this is
yes,
1 by
ma'am. Yes,
j.
ma'am.
So this 1 by j is again minus j, which will be cancelled out with this minus j. Right? Because the capacitive, the impedance of the capacitive branch is R minus jXc. How do we represent the capacitive, the impedance of the branch of any branch having the capacitance? What is the impedance of this branch? How do we express impedance of this branch? It is just equals to R
One by.
minus jXc, right? R minus jXc. This is the form R minus jXc, where in case of inductive reactance, branch having inductance, will express impedance as R plus jXc. JXL, sorry. R plus JXL, correct? So this R minus JXC, R part is 0. So impedance is just minus JXC, right? Impedance is just minus JXC. And what is the current? Voltage by impedance. That's why I have written V by minus JXC. True? Now this 1 by J is now minus J. And that minus, this minus will be cancelled out. So you have only JV and omega C. Clear?
Yes, sir.
Okay, now with this I1 and I2, we will find out the total current I. So this is the final expression of the total current, which is having real part and imaginary part. If you extract the real part and imaginary part, you will be able to calculate the magnitude of this current I mod and the angle of this current, phase angle of this current, angle I, which is tan inverse of P by A. And magnitude is square root A square plus B square. And what is A? A is this one. If you represent this current in rectangular format, what you will get A plus JB, where A is the real part and B is the imaginary part. So extracting the real and imaginary part with respect to R, L, V, etc., you'll be able to calculate its coefficients A and P. From there, we'll be able to calculate the magnitude of the total current, okay? Because here, total current is the sum of the two individual branch currents, because we are dealing with now parallel circuit. Okay, so now again we'll apply the concept of resonance here. XL will be equals to XC. XL will be equals to XC, or omega naught L will be equals to 1 by omega naught C, right? So applying this, we'll get the expression of resonating frequency F naught. Okay, and finally from there, we'll be able to calculate the current and impedance curve. So here we see that current is minimum at resonant frequency F naught, because impedance is maximum at resonant frequency. And what is the value of impedance F naught? It is L by CR. It is L by CR. And this will be calculated from this. Okay, because this is the parallel circuit. This is the parallel circuit. This one, right? So if you find out the total impedance or the equivalent impedance, you will see that from this, the omega naught will be calculated as 1 by L under root L by C minus R square. Okay,
Ma'am, what is B?
Yes, ma'am.
B is the coefficient of this imaginary part. V omega C minus V omega L by this. This is the expression, final expression of current in rectangular form, having the real part and the imaginary part. Real part is here small a and imaginary part is here small p. Okay, now at resonance, what is the phi? We have seen the phasor diagram earlier for a series circuit. Right? So in resonating circuit behaves as a purely resistive one. So there is no phase difference, there is no phase angle in between voltage and current, right? So what will be the value of this phase angle? At resonance, it will be 0. Now it is tan inverse of B by A, right? So if tan inverse of B by A is 0, B is definitely equals to 0. Now if you equate this B of V omega naught C equals to 0, what you will get? You will get this expression. And from there, you will be able to calculate omega naught, which is 1 by L square root L by C minus R square. Yeah?
Ma'am, we can also see from the power factor that it is 0. Sir, ma'am, because cos phi will be R by R, that is 1. So cos 0 is equal to 1. So
No,
phi
no,
is
no,
equal to
no, 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 no. No, it's not a series circuit. So impedance is not just equal to R. So we can't this thing from power factor.
Okay, okay, ma'am.
Impedance is just not equals to R, like the series RLC circuit. Okay.
Yes, ma'am, understood.
Power factor is R by Z. Always power factor is R by Z. Now in case of RLC series circuit, Z is equal to R. That's why power factor is taken as a unity for RLC series. Okay, but this time in case of parallel circuit, you have to start this derivation from phase angle during the resonant frequency. It is it is 0. There is no phase angle. It is 0. That's why V is 0. So if V is 0, we'll calculate omega naught from this as 1 by L. Previously it was 1 by root LC. In case of series circuit, it was, what was the expression? It's just 1 by root LC. Omega naught and F naught 1 by 2 by root LC. So this time for RLC parallel, considering this topology only, RL in series, which is in parallel to C. If you consider individual R, L, C in parallel, then definitely you will get this parameter different from this value. Right? So from this, we'll get again one more condition, that is omega naught C is equals to 1 by omega naught L. Equating B equals to 0. Right? Okay. So where this omega naught C is defined as the capacitive susceptance and 1 by omega L is called the inductive susceptance, because XL is the inductive reactance and susceptance is just the opposite of reactance. So definitely 1 by XL is called the inductive susceptance and 1 by omega C is called the capacitive susceptance, because 1 by omega C is called the capacitive reactance. Okay. So with this, we will again calculate I naught, and which is VRC by L. How? See, I is A plus J. So at the resonating condition, only at resonant
Ma'am,
frequency,
your
current value can be
voice.
represented as this. What?
Ma'am, your voice is cancelling.
Now it's okay?
Yes, ma'am. It's okay.
Now is it okay?
Yes, yes, ma'am.
Okay.
Yes, ma'am.
So just look at the expression of this current. It is just A plus JB, where B is taken as 0 earlier, right? Because imaginary part goes down to 0 at resonant condition, considering 0 phase angle between voltage and current. So this is the final expression of current, only the real part. And this is the value of omega naught we have derived already for parallel RLC circuit at resonance. Now with this further, you will get this expression of I naught. See, it's VRC by L. It's VRC by L. Okay, that means at resonant frequency, the current value is I naught, which is VRC. V voltage, R resistance, C capacitance divided by inductance. All are constant. So this is the value of current. So now with this value of current, we'll further calculate the value of impedance, because impedance is simply V by I, V by I naught. V by I naught is called the impedance at resonant condition. Okay. Now this is the value of impedance, R plus omega square L square by R. So it's not just equal to R. Fine. So that's why impedance will be definitely maximum at resonant frequency. So further we can reduce the expression of this Z naught. It is R square plus 1 by C minus R square by R. So further it is represented as L by CR. Okay, simplifying this. So here, finally, what we can conclude from parallel resonating circuit or from parallel resonance? First thing, reactive component of current is 0. The capacitive susceptance is equal to the inductive susceptance. Phase angle between the supply voltage and the supply current is 0. An inductor impedance does not have any, it's purely resistive, right? Because the total inductive susceptance will be cancelled out by the total inductive capacitive susceptance. So circuit has only the resistance part, so definitely circuit will operate at near unity factor, unity power factor, and supply current is minimum and the effective impedance is maximum. We will be able to calculate the power factor cos phi from this. This is the expression of Z naught, right? And you know power factor cos phi is R by Z from impedance triangle, right? So you can check what is the value of power factor cos phi from the impedance triangle. This is the expression of impedance. Again, in case of parallel circuit, you can calculate quality factor, which is just the ratio of IC and I naught, the capacitive current and the current during resonance. So Q is just omega L by R, or this 1 by R root L by C. And also in the form of bandwidth. This is resonant frequency and this is the bandwidth, omega 2 minus omega 1. So same relation will be applied to RLC parallel circuit also. Okay, next coming to the generation of sinusoidal voltage for three-phase system. So we have already seen the generation method of a single phase sinusoidal voltage It's in a single coil, a bar type conductor under the field having north pole and south pole, where constant flux lines will be flowing from north pole to south pole. And if the coil is made rotating under that magnetic field, then by applying Faraday's laws of electromagnetic induction, the flux lines will be cut by the conductor, which will create EMF. So instead of putting a single conductor, if we place 3 conductors, 120-degree displacement by each other, 3 sinusoidal voltage can be produced. Sorry. Shown in this diagram. So this is the first conductor. This is the second conductor, the blue one. The red one is the first one. Blue one is the second one, and green one is the third one. Okay. And these lines are the flux lines flowing from north pole to south pole. Okay, and these 3 coils are made rotating under this magnetic field, common magnetic field. And these angles are 120. That means this blue colored coil is displaced by this red coil under the magnetic field. This green colored coil is placed with 120 angular displacement with the blue one and 240 angular displacement with the red one. So if these 3 coils are rotating under this magnetic field, again 3 sinusoidal voltages will be developed. One will be across this R coil, one will be across this blue coil, one will be across this green coil. Fine. So let us assume that this red colored coil is creating the reference sinusoidal voltage, and that will be expressed as Vm cosine omega t. So instead of representing that periodic signal, that alternating voltage signal with sine wave, I have taken cosine wave, because cosine wave is also alternating in nature and it's a periodic signal. So I have represented the first voltage due to the red coil as Vm cosine omega t. Right, and I have assumed initially that there is exactly 120-degree angular displacement between each coil, and they are having at same magnitude. That means the system is balanced. Your 3-phase system is balanced. We have 3 phases. That means the magnitude of all 3 periodic signals, all 3 alternating voltage signals are having same magnitude, same peak, Pm, and they are making exactly 120-degree. 3 coils are 3 conductors are making exactly 120-degree angular displacement by each other. Next comes this Va. This is across the first coil, this red colored coil. In Va, I have taken Vl. So that I'll explain later on. What is the XV and VC? So for the timing, just understand that this magnetic induction across this red colored coil and so on. So since the second coil is just displaced by 120 degrees by 120 degrees, that means there is an angle of 120 between these 2 coils. So definitely the voltage developed across this coil will be represented cosine omega t minus 120 degree. Similarly, in case of third coil, case of green colored coil, which is 120 displaced by blue and 240 displaced by red one. So we can represent the voltage across the third coil can be represented as Vm cos omega t minus 240 degree. Next, coming to currents. Now, due to these three alternating voltages, definitely three alternating currents will be produced, right? And considering lagging power factor type load, always currents will be lagging by the voltages. Now, if the reference voltage is Vm cos omega t, what will be the reference current signal expression? It should be definitely Vm cos omega t minus theta. Theta should be the phase angle between the voltage and the current, considering lagging power factor load. If it takes VAN as the reference vector, definitely this will be IAN, the reference current vector, which is making an angle of theta, which is called phase angle. Because in case of lagging power factor type load, in case of inductive load in industry, mainly all the loads are of inductive type. So considering that, definitely I current will be lagging by the voltage by angle theta. Okay. So definitely the current expression will be denoted as Im cos omega t minus theta. And since the two coils are displaced by the reference one by 120 and 240 degree respectively, current flowing through the second coil can be expressed by Im cos omega t minus theta minus 120. For the third coil, it can be represented minus 240 degree. Is it clear to everyone? And since we are considering the balanced system, balanced three-phase currents, definitely the current signals must be displaced by 120 each other, and the magnitude should remain same as Im. Is it clear to everyone? Any doubts up to this?
Ma'am, why that is minus the phase difference?
Which part?
Ma'am, you have written
This part.
omega t minus no ma'am voltage part.
This one.
Yes, ma'am. Why it is minus
See,
120?
because the three coils are placed 120 degree displacement by each other. Just a minute. Because three coils are displaced by 120 by each other. It is the convention for the generation of three-phase alternating EMFs. Always we need to place three conductors, three coils under the magnetic field, each displaced by 120 by each.
Okay, ma'am, understood. And ma'am, what
Okay.
is its use? Generation of three-phase AC.
Generation of three-phase alternating current signal. AC stands for alternating current. Alternating current signal. Okay, so we need to design the position of these three conductors under this magnetic field in such a way that they will be making an angle of 120 by each other. We'll see those different connections, how to connect these conductors or windings under a magnetic field, how to place the conductors or coils, how to design them, design the connection between them. But to make a balanced system, always there should be an angle of 120. So definitely the signals, the alternating signals will be displaced by 120. If Vm cos omega t is the reference one, definitely the second one will be displaced by 120 and third one will be displaced by another 120. That is in total 240 degree. Right? Now again, the three currents generated due to these three alternating voltages will be displaced by 120 by each other. And since we are considering only the lagging type load, that means only the inductive type of load, where current is lagging by the voltage. So the first current generated because of this VAN will be lagging by this voltage by angle theta. So that's why I've taken the first current as Im cosine omega t minus theta. Rest 2 will be displaced by again 120 by each, by the reference. The second one can be expressed as Im cos omega t minus theta minus 120, minus 240. Clear?
Yes, ma'am. Clear.
Okay, if I draw the phasor diagram containing all three currents and all three voltages, then definitely you'll be having a better idea. Let me draw it if possible. Say this is VA. Let me check. No, the diagram is not there. Let me try it. It's a simple phasor diagram. Say this is VA, this is VB, the three alternating voltages, and this is VC. Definitely the magnitudes should remain same. VA, VB, VC. Okay. Now, due to this VA, this IA currents will be generating. This is 120, right? This is 120. Now, since we are using lagging power factor type load or inductive type of load, IA, the current generated due to this current, due to the voltage VA, will be lagging by the VA by angle theta. Okay. Similarly, the current generated because of the voltage VB will be lagging by the voltage VB by an angle of theta, same theta. And also the current generated due to the voltage VC, that is IC, will be making an angle of theta because of inductive loop. Okay, so if we want to express the signal mathematically, the current signal IA, what I should write? Im into cosine omega t minus theta. Clear? Now in case of IBT, what should I write? Omega t minus theta minus 120. And for IC, it is omega t minus theta minus 240. Clear? I need to follow a phasor diagram. Yes.
Ma'am, can I ask one thing?
Yes, sure.
Ma'am, why minus 122 theta instead of minus? We can write plus 20 degree also.
No, no, because look at this phasor diagram properly. This VA is taken as the reference one. VA is taken as the reference one, say Vm cos omega t. Now, VBN is just lagging by this VAN by the angle 120. Right? Because we are rotating in the clockwise direction. So taking clockwise direction as the positive, considering clockwise direction as the positive sense, what we should say that VAN is ahead of the signal VBN. Or we should say that VBN is lagging by the signal VAN.
Okay, ma'am, understood.
Okay. That means VB is lagging by the angle 120 because it is placed just 120 degree displaced by the first one, VA. That's why it's 120. And further, this current IA is making an angle with this voltage VA because the load is inductive type. Initially, we have assumed the load is inductive type, right? Or the lagging power factor type. So always the current signal will be lagging. So due to this voltage VA, the current IA will be expressed as cos omega t minus theta. Okay. Now this minus 240 can be further represented as plus 120. That is the separate issue. Now phase sequence. Phase sequence. If we follow these guidelines, that means considering VAN as Vn cos omega and VBN as omega t minus 120, VCN as omega t plus 120, what is the phase sequence? In polar format, VAN as Vm angle 0, VBN as Vm angle minus 20, and VCN as Vm plus 120. Right? So considering this, and in this side, expressions, we can say that if this is the Vn, the reference one, VBN is displaced by 120 and VCN is also displaced by another 120 or 240. Okay, so what is the sequence? What is the sequence? It is A, B, C. It is A, B, C. Or you can say it is A, C, B if you consider this side rotation. You can say that the sequence is A, C, B. Whereas in this case, see, the sequence has changed. It is A, B, C. It is A, B, C. Why? Because for this type of phase sequence, what I have assumed? I have assumed that the reference one is Vm angle 0. VBN is Vm angle plus 120. That means plus 120 means minus 240 degree. That means this time VBN is displaced by minus 240 degree by A. So look at this figure. This angle is 240. This angle is 240. So plus 120 means actually minus 240. That means VBN is displaced by 240. So if you change this angular difference, the phase sequence will be also changed. So depending upon this angular differences, phase sequence will be dependent. Next, calculation of power. The instantaneous power for a three-phase circuit can be calculated as PA plus PV plus PC. PA is the power generated because of the first coil, PV for the second coil, PC for the third coil. And for a single coil, we have checked the power calculation. It's Vm Im by 2 into cos theta. So three-phase power is just nothing but 3 Vm Im by 2 into cos theta. Now this Vm by 2 can be represented as Vm by root 2 multiplied with Im by root 2 in this expression of power.
Why one of the angles was taken in clockwise?
Which one? This one? This figure?
Yes, ma'am.
What are you talking about? Yes, what is your question?
Why one of the angles is taken as clockwise?
This angle. This,
Yes, ma'am.
this signifies that if you rotate in this side, it will be considered as plus 120. If you rotate in this side, it will be considered as minus 120. Nothing else. Since in this diagram, it has shown that omega is in the clockwise direction, sorry, anti-clockwise direction, right? So it means that VCN is equal to Vm cos omega t plus 120. This depends on type of rotation you are assuming initially. Okay.
Okay.
Okay, so reducing this Vm by 2 as Vm by root 2 and Im by 2 as Im by root 2, final expression of instantaneous power is 3 Vrms Irms into cos theta. That means the total power is 3 times S5 and it is known as three-phase power because in this system it has got 3 phases. right? So this time it will be called as three-phase power. So these are the notations mainly used in three-phase circuits. Phase current is I phi, line current is IL, phase voltage is V pi, and line voltage is VL. So in electrical engineering, these four-way systems are very important, right? We have basically two types of systems, electrical systems. One is called the three-phase three-wire systems, and the second one is three-phase four-wire systems. So in case of three-phase three-wire systems, we have only three phases, just like this figure. We have only three phases: phase A, phase B, phase C, right? But in case of three-phase four-wire system, another wire is required to connect. Okay. So why it is required, this four-wire system, three-phase four-wire systems? Let me draw the phasor once again. This is A, B, C, three-phase three-wire systems. It's a three-phase system and only three wires are used. So it's called three-phase three-wire systems. And we have assumed that the magnitudes of the three voltages are same. The peak magnitudes are same. That means it's a balanced system. Now, if there is any unbalance, like how the unbalance can be met. Suppose this angle is not made 120 exactly, it's 110 or 130, or if the magnitudes are not equal by each other. So one is called VM and say 100 volt, and another one is having 110 volt, and the third one is having 130 volt. So this type of systems are called unbalanced systems. Now, if the system is balanced, then what will happen? The sum of the three currents flowing in these three coils will be equals to zero. Just apply the KCL law. If three currents are flowing in this direction, sum of the three currents I1, I2, I3 will be exactly equals to zero. It's a three-wire system. Right? Now, if any unbalance occurs, then what will happen? Sum of the three currents will not be equals to zero. Right? I1, say I1 plus I2 plus I3 should not be equals to zero if any unbalance occurs, right? So due to that unbalance, what will happen? There should be another path required through which that unbalanced currents can flow, right? So this is called three-phase four-wire systems, and this is only used in case of unbalanced system. Whenever there is an unbalance, that unbalanced current, right, must be flown through some other path, which is called the neutral wire. And this is the fourth wire in the system. So this is called a three-phase because it has got three phase only. Four-wire system due to this addition of neutral wire, right? So if the load is balanced, if the current in the neutral point is zero, definitely this type of four-wire system is not required, right? But if there is any unbalance, we need to pass that unbalanced currents through some wire, which is called neutral wire. So that is called three-phase four-wire systems. So what is called, yes, tell me.
What is its practical example in real life?
Unbalanced load. Unbalanced load. Unbalanced load means if in all the three phases, same currents are not flowing or same voltage is not there across the three coils, across the three conductors. It may happen for any type of three-phase load. Due to any types of disturbances, any types of faults, this unbalance may occur within the system, within any electrical system, right? So definitely there should be a provision of this four-phase system, but simultaneously if you are adding this extra wear. So this electrical system design cost will be increased. Cost will be increased if you use three-phase forward system, right? But mainly this is required for larger currents, larger systems. For smaller value of currents, definitely there should not be the possibility of this unbalanced current, because we should always use balanced system. It is not desired to have unbalanced within the system. Okay. Next, what is called the phase voltage? It is measured between the neutral and any line. So this point is called as the neutral point, where all three conductors are joined. This is the common point. This is called the neutral point. Now, when you are measuring the voltage across this point, C and neutral, it will be called as phase voltage. And if you measure the voltage across this and this, it will be called as line voltage between the two lines, because these are lines, three lines in three-phase system. So when you are measuring the voltage with respect to this neutral, it will be called as phase voltage. When you are measuring voltage difference between the two lines or between the two phases, it will be called as line voltage or line to line voltage. Okay, so this VAN is nothing but called as phase voltage, right? Because it is the voltage between that phase itself and the neutral point, or the common point where all three phases are meeting. Clear? Do you have any questions up to this?
Can you send this PDF?
Yes, after completion of this entire module, I'll send this to the classroom.
But it is difficult to revise without
Yes,
this.
yes, sure. By this weekend, I will send it to you. Don't worry. Because we are almost at the end of this module. A few derivations are there at the end. So how much time we have today? Time is over. Okay, do you have any class now?
No, ma'am, we don't have
No,
any class.
ma'am.
So shall I complete this module? If
Yes,
you allow me.
Yes, ma'am.
No problem.
Okay, so we'll finish this chapter. So next week I'll start with a new module. Fine. Yes. So these are the definitions of phase voltage and line voltage. And similarly, line current is the current in each line, and phase current is the current in each phase. Right. So you will understand this thing later on. And what is the difference between this line current and phase current? But just let me know whether you have all understood the difference between phase voltage and line voltage. Yes or no? Difference between phase voltage and line voltage. Okay. Let us see the connection, type of connection. So any electrical circuit must have a source and a load. So without having the source and load, this electrical circuit will not be completed. Right? Suppose you want to rotate a ceiling fan. You need the supply, you need the source voltage, AC source voltage, right? So this ceiling fan is your load. Okay, and source is the single phase 230 volt 50 hertz AC mains, right? Now, always we need to design our source structure and the load structure with a suitable connection, and these connections are called as, say, Y connection, delta connection, etc. Right? So Y is actually a star connection, right? Y is just like a star connection. So the layout of the connection can be either YY, Y delta, delta delta, and delta Y. So it is very much convenient to have star connection at the source side, right? And at the load side, it is always better to uh, apply the delta connection, because in the delta connection, what happens? Um, let me show you the definition first. In delta connected sources, delta means just a triangle, just like a triangle. So circulating current may result in the delta if the three-phase voltages are slightly unbalanced. Look at the diagram. This is called the star connection. This is called the star connection or Y connection. See, in star connection, three lines are there meeting at a common point, and this system has the fourth wire, which is called the neutral wire. That means all similar terminals, say all final terminals of the three coils are joined at this common point, and rest will be connected to the mains supply. So this type of connection is known as Y connection or star connection. See, look at the coils. These are actually the impedance of the three coils, ZY each, because they are balanced, right? Say ZY ohm. They are connected in star. That means all the final terminals of these three coils will be connected at a common point, or the terminals will be shorted at a common point. So this type of connection is known as star connection. See, all the three currents will be equals to 0 at this common point, at this neutral point, if they are balanced. And what about the delta connection? This is called the delta connection. See? The three lines are connected in delta. The three phases are connected in delta. This is the source side connection actually I'm showing you. That's why these three symbols are source symbols. And previously it was impedance ZY. That means that was the connection for the load side. Okay. So here these A, B, C, these are the three lines, three supply lines which are coming from the supply side. And your load, I mean this side, your source side is delta connected. So there may be a circulating current inside this delta. There is a possibility of circulating current. Okay, and how they have joined? See, the first. So for example, the second terminal of the coil AC is joined with the first terminal of PC, and so on, just like this. This is the delta connection of the load having Z ohm in each branch. And these three are supply lines ABC. Fine. See, here, let me simplify the diagram. Wait. So this is the first coil, first conductor, and these are the conductors to be placed under that magnetic field. Right? So what I will do, say the terminals 1, 2, marked as 1, 2, 1, 2, 1, 2. So in case of star connection, what I will do, I'll short all these second terminals with the neutral point. And these three lines will be supplied to the supply, the source side. And in case of delta connection, what I will do, I will join this first terminal, the second terminal of the second coil, first terminal of the second coil to the second terminal of the third coil, and first terminal of the third coil to be connected to the second terminal of the first coil. This is called the delta connection. So if you follow this diagram shown in this slide, the second one, you will get to know how actually the delta connection is made in my figure. Okay, so if you follow this uh, figure, you will see that here, can anyone tell me how to calculate where to put the voltmeter if you want to measure the line current for this type of delta connected load? Where should I connect a voltmeter to measure the line current or line voltage? Line voltage means the voltage between two lines. A, B, C, these are three lines. These are called lines. So if you want to measure the voltage between these two lines, A and B, you will connect the voltmeter over here between A and B.
Series.
Between A and B. Between these two lines, you will put the voltmeter. If you want to measure the line voltages between these two lines.
Yes, ma'am.
Okay? Okay? And if you want to measure the line current, you will put an ammeter over here to measure the line current. So here in case of delta connected load, if you want to measure the phase current, where you put the ammeter, you will put ammeter over here. Right? To measure the phase current, because these three are called phases and these three are called lines. Three conductors will constitute the three phases, either in delta mode or in star mode. Fine. So if you want to measure the phase current, you will put the ammeter over here. Now, have you all understood the difference between line current and phase current? Moving to the star connection once again. Where to put the ammeter? To measure the line current, you will put the ammeter over here to measure the line current. And where to put the ammeter to measure the phase current? You will put the ammeter over here. So in this type of connection, in star connection, in Y connection, definitely there is no difference between line current and phase current. They are same. Line current is equal to phase current in case of star connected system. And that can be derived mathematically also. Okay? And in case of delta connected system, if you want to measure the phase voltage, where you will put the voltmeter? Where you will connect the voltmeter if you want to measure phase voltage? You will connect the voltmeter across these 2 points. Suppose you want to measure the phase voltage of this phase. Here you will place the voltmeter across these coils. So placing a voltmeter here across this coil like that and placing it in between these two lines are same. That means for delta connected system, always the phase voltage is equal to line voltage, and that can be also proved or derived from the mathematical expressions. Here. Is it okay with everyone?
Yes, ma'am.
Yes, ma'am.
Okay. Now how to prove this? Look at this phasor diagram minutely. I have taken this VAN as the reference one. What is VAN? The phase voltage of the first coil, which was expressed as Vm cos omega t earlier in the beginning of three-phase system. I have explained that. Why Vn is Vm cos omega t. Can you remember that? Now, what is VBN? It is this system, this phasor diagram is following the phase sequence as A, B, C. Say I have taken the clockwise rotation. Right? I have taken the clockwise rotation. So this VBN just 120 degree displaced by VN, and this VCN is just 240 degree displaced by this VN. Right? So these are the three phase voltages, VN, VBN, and VCN, measured across the phase with respect to the neutral respectively. Now, if you extend this VBN phasor, this red colored phasor, in the negative direction, what you will see? Just express it. And remember, this is a balanced system. That means all three magnitudes, VA, VB, and VCN will be same. And this angle will be 120 degree exactly in all the cases. Now, if you extend this VBN in the opposite direction, what you will get? You will get minus VBN. So I have drawn this one, this vector as minus VBN, which is just parallel with this. So either with this shifted minus VBN, you complete the triangle, or with this extended VBN, you complete the parallelogram. So whatever be the law, parallelogram law or triangle law, you will get the resultant, this green colored signal, PAB, which is the resultant. How to calculate this resultant? It is just equals to, I'm showing it for only one phase. You will do it for the rest. What is the law? VAB is equals to VAN square plus VBN square plus 2 VBN into AN VAN into cosine 60. This is 60 degree, right? So if you simplify this, you will get VAB equals to root 3 V phase. V phase. V phase. VAB equals to root 3 V phase. What is VAB? VAB is the line voltage between the two lines A and B. And what is VAN? The phase voltage between the phase A and the neutral N. And all three phase voltages are same because I have assumed balanced load. Right? So V line is equals to root 3 of V phase, and that will be obtained from the parallelogram law. Okay, and see the VL, each VL, the line voltage, lead their corresponding phase voltage by 30 degree. Look at the figure. This is the line voltage, and this is 30 degree. So each V line, you will get VCA, you will get VBC, the other two line voltages. And see, what is the angular difference again in between the line voltages? Exactly 120. That means they are balanced. Right? Now from the same phasor diagram, you can find out the relationship between phase current and line current of a delta connected system, because for delta connected system, phase voltage and line voltages are equal to each other. They are same. Just a minute. A delta system. This is called phase voltage because it's a phase, and also it's called line voltage because see, if you connect the voltmeter across these two terminals A and B, it means that you are actually connected, you have already connected the voltmeter across the two lines A and B. So phase voltage and line voltage is the same. Okay, and this is the expression. I line is equals to root 3 of I. Because what is I line? What is I line? Look at the diagram once again. What is I line? This is I line. IA, IB, IC, these are line currents. This is the source side, this is the load side. Suppose a delta connected source is connected with a delta connected load over here in this diagram. So these IA, IB, IC are line currents. These are balanced currents. So definitely their magnitudes will be equals to same, equals to IL. So So if you want to measure this line current IL, what you will do? It will be obtained as IAB minus ICA. What is IAB? This is IAB. What is ICA? This is ICA, right? Because this current IA is entering to this node A, and these two, see, IAB is leaving and ICA is also entering the node. So apply KCL at this node, also at this node, also at this node. You'll be able to find out IA, IB, IC, 3 line currents separately,
Ma'am,
like this. Yes.
ma'am, actually, I'm not feeling well. So, ma'am, actually, I'm getting fever, I think so.
Okay, okay. No issues. What is your roll number?
Ma'am, 36.
Okay. You may leave.
Okay, ma'am.
Okay.
Okay, ma'am.
So IA, this line current can be calculated as the difference between IAB and ICA. Look at the notation, ICA. Right? Similarly, IAB is equals to IBC minus IAB. IBC minus IAB. Fine. Similarly, IC equals to ICA minus IBC. ICA minus IBC. So these are the expressions of line currents, IA, IB. Whereas in case of star connected system, all 3 line currents were equal to the phase currents. Go back to the system once again. This is the system. What are the line currents? IA, IB, IC. Right? Now what is phase current? Current flowing through this phase, this phase, this phase. So they are same. The line current and phase currents are same. Okay? But in this case, look at the phasor diagram in order to find out the relationship between I line and I phase. Look at the phase current phasor first. IC, IB, IA. These are the phase currents. These are the phase currents. Now with these 3 phase currents, if you draw either the parallelogram or a extending, say for example, you want to find out the line current ICA. So to get the line current just a minute. No, not ICA. Suppose you want to find out the current IC. IC is the line current. IC, this current you want to find out. So what you will do? You will first take the 2 phase currents. Which phase currents? CA and BC. So this is your CA, this is your BC. What are these things? Phase currents. Look at the phasors minutely. This is the ICA phasor. This is IBC phasor. With these 2 phase currents, you'll be able to calculate the line current IC. What you will do? You will just extend this IBC in the opposite direction, and you will complete the parallelogram like this. You will get the resultant IC. Clear? That means for delta connected system, you need to draw the phasor diagram in order to find out the relationship between IL and I5 with the phase currents as the reference phasor. And in order to find out the relationship between VL and V phase, for the star connected system, always you want to consider the phase voltages as the reference quantities. Now, have you all understood these things?
Yes, ma'am.
Okay. Now with these 3 phase currents, you'll be able to calculate these 3 line currents, IA, IB, IC. And line current is just equal to √3 times I phase. Just complete the parallelogram. How to calculate the magnitude of IC? Square root ICA square plus IBC square plus 2 ICA IBC into cosine 60 degree. Okay, and here ICA, IBC, IAB all are equal because the system is balanced system. So all the magnitudes are equal, so equals to I phase. So finally you will get √3 I phase. I line is √3 I phase. Okay, so I line is √3 I phase. Always for delta connected system. And you look at the phasor diagram once again, you will see IL is lagging by the corresponding I phase by 30 degree. This is the line current. See, always this line current is lagging by this phase current by 30 degree for all the three phases. This is one of the properties of the delta connected system. That's it. So by this weekend, I'll send this, by today only, I'll send this PPT to you, students, so that you can go through this in this weekend. So probably when we'll meet again on Monday, we can discuss on AC fundamentals related to your doubts and queries. And on next Tuesday, definitely during the tutorial class, we'll solve numerical problems from AC fundamental circuits. So you should go through the entire PPT before coming to the next class on Monday, so that we can discuss your doubts. Is it clear to everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, let me take your attendance. Okay, now please let me know. Do you know your roll number? Because the new roll sheet has been formed. So do you know
Yes,
your
ma'am. We've got our roll number.
Yes, ma'am.
Yes, ma'am. We know our roll number.
you know your roll number? Okay, today I'm calling out by your names. From next week, I'll call your names with your roll numbers. Okay, so next today I'm calling out your names. Srinita,
Yes, ma'am.
Orgodi,
Present, ma'am.
Oniddo,
Ma'am.
Uishi,
Present, ma'am.
Atul,
Present, ma'am.
Manik,
Present, ma'am.
Shiab,
Yes, ma'am.
Raj,
Present, ma'am.
Shubrani,
Present, ma'am.
Ninadri,
Present, ma'am.
Aditya, Aditya,
Banerjee or Ghosh?
Banerjee, Aditya Banerjee,
Okay.
Aditya Banerjee absent. Indrila,
Present, ma'am.
Present, ma'am.
Chorik,
Present, ma'am.
Prince,
Present, ma'am.
Shoni,
Present, ma'am.
Abir,
Present, ma'am.
Ankita,
Present, ma'am.
Sagyat Mukherjee, Ritacheta,
Present, ma'am.
Srajal,
Present, ma'am.
Kirti, Shoel.
Present, ma'am.
Present, ma'am.
Okay. Shantanu,
Yes, ma'am.
Sattam, Sattam, Ilham.
Present, ma'am.
Sattam, are you present?
Yes, ma'am. Present.
Okay. Pooja,
Present, ma'am.
Aman,
Present, ma'am.
Hindu,
Present, ma'am.
Rifat,
Present, ma'am.
Farhan,
Present, ma'am.
Soham,
Present, ma'am.
Abhijit,
Present, ma'am.
Aditya Ghosh,
Present, ma'am.
Anushrita, Anushrita.
Anushrita left, right? She has fever. She told
Okay,
you.
Anushrita is 36. Okay, okay.
Yeah.
Okay, okay. I'll mark her present. After Anushrita, Kundan.
Present, ma'am.
But Anushrita is 35, right?
Yes, ma'am. Yes, ma'am.
Yes. Okay.
I am 36.
Yes, yes. Shangita?
My roll number is 36.
Yes, 36 is, serial number is 36 for Kundan. Shangita?
Yes, ma'am.
Shangita Jha. Next, Chandrani,
Present, ma'am.
Moli,
Present, ma'am.
Harsh Ranjan,
Present, ma'am.
Chomen,
Present, ma'am.
Tejas,
Present, ma'am.
Mrinal,
Present, ma'am.
Lisan,
Present, ma'am.
Shagdi, Ghoshal,
Present, ma'am.
Farzina,
Present, ma'am.
Abdi,
Present, please, ma'am.
Shagnik Biswas, Shagnik Biswas, Riddhi,
Present, ma'am.
Shubhajit, Pratik,
Present, ma'am.
Mohammad Zain,
Present, ma'am.
Arun,
Yes, ma'am.
Ahona,
Present, ma'am.
Apurva.
Present, ma'am.
Okay, thank you all. You may
Thank you,
now
ma'am. Ma'am.
Ma'am, I'm Aditya Banerjee and I was present, ma'am.
Aditya.
Serial number 11, ma'am.
11. I called your name.
Yes, ma'am. I had problem with my mic, ma'am.
Okay.
Earphone mic.
Okay. So Shagnik Mukherjee, are you there? Shangita, Shagnik Mukherjee, Shagnik Vishwas, and Shubhajit. These four students are absent today. Okay. Thank you all. You may leave the meeting now.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thank you, everyone.